This is the 2-3 notes for Calculus 1. In the previous sections, we talked about how to use graphs and tables to evaluate limits. But now we need to talk about more analytical ways to do so, which will take a lot less time. So we start with some very, very important properties of limits. Okay, these properties take hold for all the problems that you're going to work with, and they will be very helpful in computing many of the beginning limits that we talk about. So let's sort of go through just a little bit. I'm probably going to use some of the problems to show how each one of these methods works. So let me start with this guy here. All right, so it says the limit as x approaches some value c of x is always equal to c. Okay, so this variable speak can be a little bit confusing, obviously, for students. But what is this basically saying? This is saying if x approaches c, then you should be able to just substitute whatever that value is in for x in the function, and you are going to get the result, which is c, if you substituted that in. So it's a little bit hard to understand unless you're doing an actual problem. So let's just look at one. So it says the limit as x goes to -2 of the function 1/2 x plus 3. Now note, this graph will never be here. So this graph is here only for learning purposes only, so you will have to do this without a graph, and you will not have a graphing calculator. So how would we find this out? But according to this rule right here, all we have to do is for -2 right here, this is basically the value c. So we should be able to take this value and just sub right into any variable x, and whatever the result is actually the limit. So let's see if that actually works. So let's say let's put an equal sign here. So that should be equal to 1/2 times -2 plus 3. So all we did was take the -2 and sub into any value of x we see. This will be -1 plus 3, which is equal to 2. So the limit of 1/2 x plus 3 as x approaches -2 is just the value 2. So why do I put the graphs here? Because I want you to see why this works, and basically when you're done, you can see, wow, look at what I just did using analytical methods. So this is the graph of 1/2 x plus 3. And I'm looking for what's happening as this graph approaches -2. So this is the value right here. So if I approach this from the left and the right, it's going to be around here. What height are we approaching? We're approaching 2. And look at that. That is the answer to our problem. So literally all we have to do for this Roman numeral 2 step right here is just sub in the value. Now this is true across all limits. The thing is, though, with the majority of limits that you're going to find, when you sub in that number, we are not going to get the ideal result that we're looking for. And I'll explain that as we go a little bit later. Okay, so what about the next one here? So it says for Roman numeral 1. So it says that k is a constant. So it says the limit as x approaches c of the constant k will always be equal to just the constant k. So what they're basically saying is, since there's no variable to plug in here for x, then the c is irrelevant to the problem. Basically, the best way to say this is the limit of a constant is going to be a constant. So how does that apply to number 2 here? So if you look at this, if you look at this value, it says the limit as x approaches 1 of 2. Okay? So remember, this is the value of c right here, but according to this is the value of k, which is our constant. So if we follow this rule by the letter of the law, then this should be equal to just 2, because the limit of a constant equals a constant. Okay, let's see why that works. So if you look at the graph of y equals, remember, this wouldn't be provided to you. I'm just using it as a way to explain. If you look at this graph right here, remember that, let me just get rid of some of this so you can do it. So this right here is the function. So this line is y equals 1/2 x plus 3, okay? Or f of x equals either way you want to look at it. So that means that this is our function. So we need to graph fy equals 2 or f of x equals 2, which is a horizontal line for our problem. So if we go over to where this limit is approaching, which is at 1, that's going to be here. What is the height that this thing is approaching from both sides? Well, clearly, the height of this never changes because it's a horizontal line, which means this is going to be the limit of our problem. No matter what I do, the limit is going to be 2. Hence why the limit of a constant is a constant. Okay, so hopefully that I'm hoping that you understand that fully, that has to be the case in these scenarios. Now, it turns out that this works for pretty much any problem. So notice here we had a linear function. So let's just say that we now go to 3 and we have a more polynomial type function than anything else. So we have a degree 3 polynomial sitting here, but the rules still apply. So this right here is the graph of f of x equals 2x cubed minus 5x minus 2, right? So this is what the graph looks like for when we check it later. So, but according to the rule, all we have to do is sub in whatever this value is for every value of x. So if we go down here, this should be equivalent to 2 times 2 cubed minus 5 times 2 minus 2. If we put that in and do a little bit of computation, we are going to get 4 as our result, which means the limit of this problem is 4. Well, let's see if that checks out with our graph. So we're approaching 2, which is right here. So if we approach 2 from both sides, look at the height that it's approaching. In other words, what is the value of y? And remember, whenever we find a limit, the limit is always equal to the value L of our problem. You can see it's right here, of the limit when we go through the problem. So it's very interesting that like this seems to work for all expressions. So, well, we've done, let's see, linear, right? We've done a constant. We've done polynomial. Let's try rational now. So for a rational function, well, let's check that out. Well, it looks like v, a Roman numeral for v, which is 5, looks like we have a rational function. According to this, all we have to do is plug in c into our functions, just like we normally would do, and whatever the limit is just going to be the limit of the numerator over the limit of the denominator. So that should be okay. We should be able to handle that. So once again, though, what do? We just take this and plug it into the numerator and plug it into the denominator. What do we get? We get negative 1 minus 1 over negative 1. This is going to give us negative 2 over negative 1, which is just 2. So the limit of a rational function is the limit of the numerator, which is negative 2, over the limit of the denominator, which is negative 1, which gives us exactly 2. So what does our typical rational function look like? It looks like this. So let's just verify. So our limit is approaching negative 1. So if we go over here to negative 1, and we approach it from the right and the left to look at the height in which we are approaching it at. We're approaching it at 2. So I do this on purpose. I go through a bunch of problems that are similar, and I like to show on the graph afterwards so you can see exactly what you did and that these rules work just fine. Now, Roman numeral 3 right here is basically also applied to these types of problems, just so you know. So anytime you have a value with a plus or a minus between it, then that allows you to plug into every single value as you go. So basically for 1 and 2, we were using a combination of these two rules when we were applying it. But the other rules basically say that this works fine with products and roots all the way through. All we have to do is sub in the value and we are all good. Okay, it turns out that in calculus, in 1, 2, all the way up, a special type of function actually is used fairly often, and it actually is a really good example of how to apply limits, and those are piecewise functions. What are piecewise functions? They are functions that take on a different function depending on where it is on the graph. Here is a perfect example of a piecewise function where you usually see this bracket right here in order to show that it's making up several functions. So what is going on here? So this function is takes the form of negative 2x plus 4, which is a line, anywhere before the value of 1 for x, including 1. Whereas then, for every value strictly bigger than 1, it takes a square root function. Okay, so the best way to really understand piecewise functions is to graph them before you do anything. So we'll graph it first. So basically the cutoff, if we number this a little bit here, so let's do 2, 4, 6, do a scale. Remember, always put scales on your graphs. A lot of students forget to do that, and that's never a good thing. So always scale your graphs so that we know what's going on. So let's say we, for every value less than or equal to 1, so basically 1, which is right here, we are going to graph the line negative 2x plus 4. So how do we graph the line f of x equals negative 2x plus 4? Well, remember, this is m and this is b, so the y-intercept is 4. So this line crosses at 0, 4, and the slope is negative 2. So rise over run would be 2 over 1, but in the falling direction. So if you do, rise 2 over 1, we get a point here. Another, rise 2 over 1, we get something here. And what we can do is we can draw a line. But remember, we are ending at 1. Okay, and it's less than or equal to. We'll talk about that in a second. So if we draw a line, we go to about right here. Right? That's our line. I hope this is probably going to erase it. Nope. Oh, good. Okay, so that one on. Now note, because this is less than or equal to, what's going on here? Is this going to be a full circle, or is it going to be a, oh boy, or is it going to be an empty circle? Well, remember, anytime we have a less than or equal to, we always have a filled in circle. So right now, this is the graph of f of x. We'll actually, what we'll say for this to make it a little bit clearer. This part of the graph is y equals negative 2x plus 4. Okay, so what about the other side? We're doing a square root function. So the square root function also starts at 1 but doesn't include it, so there's going to be an open circle. And then we just basically have to plot this sucker. So let's say, let's take our first value at 1. If we put 1 into our function right here, 1 minus 1 is 0, the square root of 0 is 0. So our first point is literally at 1, 0. If we put in 2, 2 minus 1 is 1, square root of 1 is 1. So 2, 1 will put us right here. And if we put in, let's say, we want to create a square root. So let's target the square root of 4, which makes x 5. So x is 5, 5 minus 1 is 4, square root of 4 is 2. So if we go to 5, 2, we get something like that. And then you can see this is creating a curvature going on like this. So if you notice, this graph, which is y equals root x minus 1 after 1, and y equals negative 2x plus 4, looks a whole lot like our functions that I provided in the previous lesson. So that's why it's interesting, is they often give you piecewise functions in order to try to conquer in these problems. Now, the graph is here, but I want to deal with the graph afterwards. So I don't want you to even look at it here, because I want you to be able to solve this without the graph. The graph is there just to check when we're done. So look at 5a. So we're trying to, for this limit, we're trying to approach this function from 1 on the right side. Okay, so what does that mean? Well, if we're approaching 1, then we should be able to replace this function with the function that exists at the value of 1 from the right side. So of these two, which one of these is occurring on the right side of 1? Well, clearly it's the orange, which is the square root function. So what does that allow me to do? That allows me to write rewrite this as the limit of x approaches 1 from the right, but I'm going to replace f of x with the actual function that is occurring at that value or coming in from that value. And just like we did in the previous problems, anytime we have a limit, we can just plug in for the value of x. So we can now take this 1, ignore the plus, sub it in, and get the square root of 1 minus 1, which is 0. So the limit of x approaches 1 from the right of f of x is 0. Let's verify that. So if we're on the right side and we're approaching, we are clearly approaching a height of 0 from the right side. Now, the reason why, I know some of you might be like, oh my god, this is so much easier, why aren't we doing this? But remember that you're not going to have that, and there's a good chance that you're not going to want to graph. What if I gave you a piecewise function with 4 functions? Like, you don't want to waste time graphing it when you can easily do it this way. So 5b, what if we're coming from the left? Well, from the left side, the only function that exists to the left of 1 is the line negative 2x plus 4. So we can rewrite this as x as the limit of x approaches 1 from the left is negative 2x of negative 2x plus 4. We can sub in the 1. We're going to get negative 2 times 1 plus 4, which is 2. So the limit is 2. So just to verify this, if we're coming down this line right here, we are going to eventually hit the value x is 1 at the height of 2. So what is that? Now that we found these limits, what is the limit, the two-sided limit of x approaches 1 of f of x? So again, if you look at these guys, they do not match, which means we clearly know that the limit will not exist, which can be verified from the graph. Okay, so yes, we used the graph, right? We graphed it. We were able to do that. We verified with the graph. But again, what if we were given a problem where we didn't have the graph? We need to be able to do this without even bothering with the graph. So that's where this problem comes in. Notice I have a 3-piece-wise function with various requirements for where the function exists. Okay, I'm not going to lie. So this can be tricky for students. Some students love this and they're like, oh my god, give me 100 of these on the exam, I can do it. But sometimes it can be a little tricky with the difference between function notation and limit notation. Not telling the difference, but how do you handle that in certain problems? Well, that is what we're concerned with. So just to be clear, this function g of x looks like it's going to be a line from anywhere less than or equal to 0. It's going to be a quadratic function, or in other words, a parabola, anywhere between 0 and 3, but only including 3, not 0. And it's going to go linear again at negative x plus 7, anywhere strictly bigger than 3. So our goal is we want to evaluate all of these expressions, functions and limits, under these scenarios. So look at 6a. We have g of 2. So essentially what we need to do is we need to find the value of the function where x is 2. Now if we had the graph, if I said something like this one, if I said what is f of 5, right? What would you do? You would go over to 5. What is the value that this graph takes at 5? It is a y of 2, right? But you don't have the graph. So you need to locate which one of these functions actually exists at 2. So if you look at this, we have this one at the top is less than or equal to 0. This is bigger than 3. So basically what is happening? This function only exists for x squared minus 2 at the value of 2. So all you have to do to find the value of y is sub in 2. If we do that, we get, again, the value 2. So a lot of 2's going on here. Just a coincidence. So that means in this problem that we know that the coordinate 2, 2 exists somewhere on the graph. That is the key. Well, let's try some others to get the hang of it. Let's say we're looking at g of 9. So on our graph, where does 9 exist? Well, that clearly only exists where x is bigger than 3, which means we have the line negative x plus 7 there. So what do? We sub in 9 for negative x plus 7, and we get negative 2 as our value. So this means the coordinate 9, comma, -2 exists somewhere on this graph bigger than 3. Some more. So what about 0? Okay, this is where you have to pay special attention. So note, the value 0 is listed here, but we need to pick the graph only where it exists. So it does not exist in the quadratic in the middle. It only exists at the top function because there's a less than or equal to 0, which means this is going to be equal to 0 plus 2, which is equal to just 2. So there is a coordinate 0, 2 somewhere on this graph in which we are actually, working through and as a coordinate. So last one, what about g of 3? Again, 3 has 2 mentions, but where is it actually only equal to 3? It's only equal to 3 in the quadratic in the middle. So that means we can then plug in 3 into 3 squared minus 2 and get 7. Okay, so basically, because we have results for all of these, okay, we know that these coordinates exist on this graph. 2, 2, 9, -2, 0, 2, 3, 7. Another small thing, note that this is called a piecewise function, which means that this is going to always have, it's always going to pass the vertical line test. So if you recall, so always remember that there's not going to be multiple values of, and when you're putting in values, you're not going to get multiple values at certain values of x and y. So just be aware of that. Okay, so let's go back to limits. So this is basically our process we were doing here. So we don't have a graph, so now we're sort of flying blind here. We have to look at this function and we have to say, what is the limit as x approaches 0 from the left side of this function? So we have to look over here and go, which one of these functions actually exists from the left side approaching the number 0? Well, hopefully you see that this expression, x is less than or equal to 0, implies that it's to the left of 0, which means if I need to find this limit, then I can rewrite this, the limit as x approaches 0 of x plus 2. So what do? Like I've always been doing, I sub in 0, add 2, and get 2 as my limit. So if I was to graph this and I was to look where the sucker is approaching 0 from the left side, it would be at a height of 2. All right, so what if we're approaching from the right side instead? So we look on our graph and go, well, if x plus 2 is from the left, we have x bigger than 0 strictly on the right is going to be this quadratic, which means we can rewrite this, the limit of x goes to 0 from the right of x squared minus 2. If we put in 0 here, we're going to get 0 squared minus 2, which is equal to -2. So the limit on that side is -2. And what does that tell us? If this is the left side and this is the right side, what does that tell us about the two-sided limit at 0? Well, 2 and -2 do not agree with each other. They're not the same, so we get does not exist. All right, so last set. So this time we're at 3. So there's no coincidence that we're listing numbers that are on the splits of each one of these. So which one of these functions is actually to the left of 3? Well, you can clearly see here x is smaller than 3 in the quadratic. So we should be able to do the limit of x approaches 3 from the left of x squared minus 2, and then take the 3 and plug it in, get 3 squared minus 2, which is equal to 7. Okay, that's our limit. What about I? If we approach 3 from the right, this is clearly to the right of 3, x bigger than 3. So we can replace our limit with the linear function -x plus 7. If we sub in 3, we're going to get -3 plus 7, which is equal to 4, which is our limit. And again, if we go to our two-sided version of that limit, we have 7, we have 4, which are not the same, so this does not exist. So do some practice with this. This is be able to do this fluently is a big deal, so make sure that is all good. Okay, so we're on page 10 here, and we're going to shift gears a little bit with a couple things of importance. Remember, at the beginning of this, we talked about this problem right here, where we had the limit of a rational function. Rational functions are the most common limit type problem or function that you actually get. Note that when we plugged in the value, we got a very clear number 2 as a result. But what if we sub in a number and we don't get a very nice result? That is going to be the key of where we are. So for example, let's just, for argument's sake, look at this right here. So let's say we have the limit of x approaches 2 of the rational function x squared minus 6x plus 8 over x squared minus 4, which, by the way, is this graph. Well, if we sub in this 2 into all values of x, like you've been already trained to do, what do we end up getting? Well, we end up, when we plug in those numbers, we get, it looks like 4 minus 12, which is negative 8, plus 8, which is 0. If we plug 2 into the denominator, 2 squared is 4, minus 4 is 0. So look what we actually got as our evaluation. We get 0 over 0. Well, that's a problem. Why? The value 0 over 0 is called an indeterminate form. It is one of the several values in calculus that don't actually have a determinate form or value that you can take. So we call it indeterminate, which means it doesn't have a value of it. So if it doesn't have a value, many students would be like, oh, DNE. No. Okay, believe it or not, if you look at this graph right now, for example, look at the limit. It's approaching 2 right now, right? So where is 2 on the graph? Right here. So if we go like this and this, does it look like the limit doesn't exist? Not in a million years. Clearly, there's a limit right there. We don't know what it is yet. It looks like it's fractional, but there's a limit that definitely exists, which means when you see something that's an indeterminate form, the answer is definitely not to conclude that it does not exist. Instead, what we have is some methods that help us deal with it. So what's our first method? Always factor and simplify before evaluating a limit. So here we go with algebra fun. So if you look at this, both the numerator and denominator are factorable. So let's rewrite the limit. And by the way, most common issue I have with students in the beginning is they just start attacking this and they completely forget to rewrite the limit. Don't do that. Be vigilant. Always write the limit and copy it as you go. So what do we got going on here? We got the limit of x approaches 2, the numerator factors, and so does the denominator. Denominator is actually easy. This is a difference of squares, right? This is, everybody should be superstars at this after all the years of algebra and pre-calc. So how do we find that? X plus 2x minus 2. What about up top? We got factoring going on there, just typical polynomials. So we're looking for basically two values that multiply to get 8, but have a sum of negative 6. That's clearly going to be minus 4 and minus 2. Okay, so why do you think we purposely wanted to factor? Because we need to simplify, right? So if we simplify, hold on one second, bugging out here. We need to simplify. We clearly know that we can simplify these two right here. So what does that leave us with? That leaves us with the limit. Again, rewrite the limit. X approaches 2 of x minus 4 over x plus 2. You never drop the limit until you actually plug in the value of the limit and find the result. And note, when we do this, look what happens. When we plug in 2 now, we actually get 2 minus 4 over 2 plus 2, which does evaluate to be a limit in our scenario. 2 minus 4 is negative 2. 2 plus 2 is 4, so we get negative 1/2 as the limit of our problem. So the key was in this problem, so it should be clear, again, where are we? So at 2. So clearly this fraction that this was approaching was negative 1/2 on the graph. Again, you're never going to be given this graph. and nor do you want to graph it. So you need to learn this method for figuring it out without the graph. But the key is that if you plug in your values and you get an indeterminate form like 0 over 0, it's the one we're going to concentrate on for now, you're going to need some other method. One of those methods is factoring and simplifying. Before we move on to the next method, I just want to be clear with one thing. So believe it or not, this graph here is actually technically a little inaccurate. So I don't know if you remember back a couple lessons ago when I was talking about there was a line that had a hole in it because the original problem was actually rational, but because of the way things canceled out, we end up with a line but a hole in it. Well, if you look at this problem, we are actually missing a hole. As I stated when I was doing the original lesson, is that software actually doesn't show holes in graphs. It just produces what the graph actually is. So what creates holes? We'll get into a lot more detail with that a little bit later, but generally it's just division by 0. So if you look at the denominator of this specific fraction, you'll see that it's x squared minus 4. So the question is what two values that plugged into this equation will create division by 0? Well, you can clearly see when we factor it here, we find those values. They are plus and minus 2. Now, if we look at this graph at negative 2, you can see that clearly there are no values of negative 2 that are actually on this graph. And if you're asking, hey, do these lines eventually touch it? No, they don't. Hopefully what you guys see here from your pre-calculus class is that this will create an asymptote. But like I said, we'll get into that a little bit more later because we're going to be talking about a topic that's directly about that. But for now, what about positive 2? So if you go over to positive 2 over here, there's clearly a line going through positive 2. That is absolutely wrong. So if you were to actually make this graph correct, you should have an open hole at 2 on the graph. Okay, so let's moving on to the next method. We have the limit of x approaches 1 of root x minus 1 over x minus 1. So again, this is going to be a method that's based on what happens when you actually evaluate this problem. So again, when we went to this and we tried to plug in 2 into all the x's, what happened? We got 0 over 0. So what happens here, if you take 1 and plug it into the numerator, you get 1 minus 1, and 1 minus 1 in the denominator as well. So this also ends up being 0 over 0. So where are we at again? We're at an indeterminate form. I'm in trouble speaking. Indeterminate form. So what do? Well, we have a new sort of strategy because if you look at this, there's no way to factor the rational expression. So if we can't factor, there's got to be something else going on, and you'll see that the key word that's coming up here is rationalize. But it's followed by something that's unfamiliar in terms of the saying. It's rationalizing the numerator. Okay, so you guys over time of algebra and pre-calculus have been basically trained to rationalize the denominator. So what does that pertain to? So let's just look at an example. So you have learned that you cannot leave a radical in the denominator like this in a final answer. So what do you normally do? You multiply by root 3 over root 3, which is the denominator, called rationalizing the denominator. Note you are allowed to do this because this is just equal to 1. Doesn't change its value. So what happens? You just multiply across. Root 9 is 3, so you end up with that as your result. So just to be clear, this is exactly the same value as this, but it's a more appropriate way to write the solution. with a radical in the numerator. So what's another one? More complicated. So what if I had something like this? All right. So let's say that, let's actually do, hold on a second. Let's do this instead. Okay, let's do that, just to do a different radical. Okay, so what can't you do here? You cannot multiply by root 2 over root 2. It's not that it's illegal, it's just it's not going to get you anywhere. Because if you tried multiplying the bottom by root 2, you're just going to distribute and add another radical to the picture. Or place a radical. You get 3 root 2 minus 2, which isn't going to do anything. So what was the strategy when it came to having a denominator look like that? Well, the key word over here is using conjugates. So the conjugate of 3 minus 2 is 3 plus 2. It's just root 2. It's just adding or changing to the opposite, the middle sign. So we would multiply by 3 plus root 2 over 3 plus root 2. Okay, so what does that do for us? Well, in the numerator, we get 3 plus root 2, because it's times 1. In the denominator, we have to FOIL, and when we FOIL, we get a 9 minus, outside is actually plus, 3 root 2, inside is 3 root 2, negative. Last is minus root 4, which is 2. So these cancel, which is the whole point of this process, and you get 7, which means that is the answer to the problem, or the proper way to write the result. Again, exactly the same value as this. You could put in the calculator to find out, but it's just a more proper way to write it. So the key here is understanding that we have basically manipulated this to get this by taking the radical and making sure that it's in the numerator instead of the denominator. So who says we can't actually go back? So you might say, well, what's the point of going back? Well, the point of going back is maybe this one for our limit is not working, so let's see if this one will. So if we go over to this scenario, we already showed that this is an indeterminate form, so that's not going to help us. So what could we do? We could rationalize the numerator and see that when we rearrange things, maybe we get something we can evaluate. So what does that look like? Well, if we rationalize the numerator, we're going to change the sign and multiply. So if we change the sign and multiply, what happens? Remember, copy the limit down, always. The numerator becomes basically a FOILed scenario. So we're going to get root x times root x, which is x. We're going to get plus root x minus root x minus 1. If you note, again, what was the point of that? It was for the middle terms to go away. In the denominator, this is where things get tricky. You will not get this problem to work unless you avoid foiling. I know that sucks because in the numerator, your whole point of it was to FOIL. But in the denominator, you do not want to FOIL. So you should be, when you study this, part of it, if you need to make a note, in the denominator, just do not FOIL that, and I'll show you why. So when you get limit as x approaches 1, remember, copy it down, you haven't done the limit yet, you're actually going to get this as the result, and hopefully you see why you weren't supposed to FOIL, because this and this cancel. If you had FOILed, that would not have shown up, and you would have been sitting there staring probably for an hour trying to figure out what to do there. So if I copy this down now, again, let's just be clear, so I'm going to do this in fancy colors. So this and this are exactly the same value. It's just I call it rearranging the deck chairs. We essentially moved it around so that we could see if there was a better way to evaluate the problem. So if I get rid of the colors here, if I plug this in, so drop the limit because I'm subbing in, do I actually get an answer? I do, which means the limit of this is 1/2. If you look at the picture, as we're approaching 1 from both sides, what does it appear the height we're approaching at is? It appears it's right here, which happens to be 1/2. And a small note before we leave, similar to this picture is not drawn entirely properly. Why? Well, hopefully it's ringing a bell at this point. if you look at this rational function right here, what is blowing this function up? The value positive 1. So if you look at this graph, there's actually a line drawn right through positive 1, which means the proper way to write this graph is with a hole in it right there. So just as a summary with that, if you get a lab problem where you have to provide graphs, let's say, and I'll show you how to do that, by the way, with software, basically you have to be careful because when you're doing the problems, your final answer, even though you're printing these out, these graphs, it's not entirely right. You must add the circle to the graph with a pencil, let's say, just to make sure you're getting full credit. Okay, so moving on, I'm going to read right here because this is important. It says, realize though that although these are the most common procedures for evaluating limits, they're talking about these procedures here, of indeterminate form, 0 over 0, they aren't the only ones. It says you might need to use some algebraic or trig manipulation to conquer some more complex examples of this. Here are some scenarios. So these are going to be more algebraic and trigonometric sort of in nature. So even though, yes, these are algebraic, but this is going to be a little bit more involved. So you're going to have to put your review hats on and make sure all is good. Again, just starting in number 7, if you plug 0 in for these x's, you're going to get 2/3 minus 2/3, which is 0, and the denominator is going to be 0. So again, what are we evaluating at? We're evaluating at this. So the thing is, though, when you look at this problem, do you see any factoring? No. Do you see any radicals? No. So you're going to have to be creative whenever you see 0 over 0 to basically achieve where you need to go. You need to use some ingenuity when it comes to knowing your algebra and trig skills. Obviously, this has nothing to do with trig. This is more algebraic. So specifically what? This is called a complex fraction. A complex fraction is any fraction within another fraction. So clearly, we have fractions within the entire fraction that we have going on here. So that is what we have to manipulate. So the question is there a way to, again, as I say, rearrange the deck chairs and move things around using legal algebraic maneuvers in order to eliminate this whole 0 over 0 indeterminate form? Well, it turns out there is, by use of what's called complex fractions and procedures for. So what do we do whenever we're dealing with a complex fraction? We always try to find the least common denominator of all of the fractions in the problem. Now, that also technically includes the denominator. I know you're looking at that and saying, no, that's not a fraction, but technically all values are fractions because it is x over 1. So the goal is that you need to find the common denominator of x plus 3, 3, and 1. So you did this in algebra. There was a whole section on it, but a lot of students will struggle to remember. But remember, in this case, x plus 3 and 3, even though you might be thinking otherwise because of the 3's, they actually have nothing in common. X plus 3 is binded together, so it's not like you can divide that by 3 or anything. It's just not. So the least common denominator of this is actually going to be 3 times x plus 3. The 1 obviously doesn't come into play because it's not a part of the process, because a 1 is a 1, right? Just like it always is. So how do you deal with complex fractions? Well, similar to when you're rationalizing the denominator or numerator, when you multiply by equivalent of 1, we have to do the same thing, but the goal is to clear the fractions. So we want to clear the fractions. How do we do that? We multiply the top and bottom by the least common denominator. Okay, so when we do that, we get a pretty big mess. A lot of students will do this mentally, and I appreciate it if you did, because that means you understand what you're doing. But I'm going to write it out because some students really struggle with their algebra skills in the beginning of the class. So I'm going to be clear. So what are we doing? We're taking 3 times x plus 3, technically over 1, and we're distributing it to both of these. So let me just put it in a different color. So we're doing 3 times x plus 3 over 1. And then we're doing minus 2/3. And again, we have to multiply that by 3 times x plus 3 over 1. Okay. Over. Then we take the x and we multiply by 3 times x plus 3. Now, technically, both of these are over 1, but hopefully you understand that you don't need to write that. If you need to in your brain to do it, that's fine, but you don't in this scenario. So, again, always bring the limit down. What is the goal? The goal is just to multiply this out. So, I'm going to use orange. So, if you look at this right here, you can see that x plus 3 and x plus 3 cancel out, which is what we want from the process. So what are we left with? We're left with this 3 and x plus 2. I'll put it where it normally goes, 3 times x plus 2. Note that the denominators are now 1, so they can be eliminated. What happens over here? Well, we have the 3's cancel out. So what are we left with? We're left with 2 and x plus 3. So 2 times x plus 3. Note the denominators are 1. So we go down here, and what do we have? We just have a very big hodgepodge. I'm just going to put the 3 in front of the x. Remember, when we multiply, we can put things anywhere, just like 1 times 2 times 3 is the same as 1 times 3 times 2. You can move things around, it's legal. So the only thing left to do here is to simplify. So we go over here. Cool, so that's supposed to be an arrow. I don't know what the hell that happened there. But limit, x goes to 0, 3x plus 6 minus 2x minus 6 over 3x squared plus 9x. Okay, so some nice things happen. The 6 and the 6 go away, and we can combine like terms in the numerator to get x over 3x squared plus 9x. Note, if you do plug in 0 now, we still get 0 over 0. So clearly something good hasn't happened yet. But note that everything in this problem is divisible by x. So we can technically cancel to get this. And then look what happens. When we sub in 0, we drop the limit. We get this, which is equal to 1/9. And that is the limit for our problem. So to be clear again, this and this guy here, believe it or not, are exactly the same thing. So when you're doing the problems, the whole point, again, rearranging the deck chairs, creating an equivalent fraction that does evaluate properly and does not become 0 over 0 for our limit, which we don't want to happen. Okay, let's try another one. So sometimes the dreaded trig is going to pop up in your valuation. I know there's one like that on the lab that you're going to be managing. So let's talk about that. So if you have trig that pops up in a problem, you still want to evaluate it. There is a good chance that in some scenarios that you're going to end up with a problem where you can evaluate it. Sometimes that does happen. If you plug in the number for x, all of a sudden you're like, hey, like, it actually works, so I don't have to do anything other than plug it in, and that's cool. It's just the point that's easy for most students. The problem is when it doesn't. So let's just talk about the basics first. So just remember, we could sub this in the calculator, but the goal of this is to know your trig, right? So this is a little small for writing on. So if you're looking at this guy, right? So 0 radians or degrees are both here, right? So that means we're dealing with, on the unit circle, coordinate of 1, 0. So when we're plugging in 0 here into both of these values, we're going to get sine 0 over tangent 0. So what is the sine of 0 degrees or radians in this scenario? It's usually radians. So the sine is always the y coordinate of, or y value of that coordinate, which is 0. So we know the sine of 0 is 0. What is tangent? Tangent is always y over x. Well, what is y over x? It's 0 over 1, which is, again, 0. So what do we have as our evaluation? We're right back to our indeterminate form again, where it's 0 over 0. So the strategies we've used already are factoring, rationalizing because there's a radical, and complex fractions. All of these have none of those in there. So a good hint usually is that there's trig involved. So what's going on here? So the goal is, back when you did, when you were in pre-calculus, and you were learning about trig identities and solving trig identities, manipulating them, proving them, whatever the word is, the goal usually is to get all of the trig functions just to be sines and cosines. Not always, but usually that's a good strategy, and in this case, that's exactly what we need. But in order to do that, remember, drop the limit, we're going to need an identity, right? So tangent x. Is there an identity of tangent x that allows us to turn it into sines and cosines? Well, let's take a peek. So I downloaded a trig identity sheet here. Even though these are in thetas, it's the same idea. You can see that in the top right over here, we have all our reciprocal identities that everyone knows really well. So one of them is here. Tangent is equal to 1 over cotangent. So that would be a valid thing to plug in for tangent, 1 over cotangent. But cotangent really is not getting us anywhere. It's not changing anything to cosine and sine. So that's not really exactly what we want. Well, if you recall, there were some quotient identities, namely this guy, which would be perfection. So remember, tangent is actually equal to sine over cosine. So if we return to our problem, we can change tangent to sine x over cosine x. Okay, always remember your variables in there as well. So just as an aside, if we did sine x divided by sine over cosine, it's the same as multiplying by the reciprocal of sine over cosine, which is cosine over sine. These wipe out, and you're left with just cosine. So this is equal, bring the limit down, x equals, or limit as x goes to 0 of just cosine x. So now the question is, if we take 0 and sub in here, and we're actually getting something good? Well, we already know that we're clear. How do we know that we're clear? Because when we did this division, we got this as our result. So what can't the denominator be in any way? It can't be 0, which means even if we did get 0 here, which we're not going to, but even if we did, we would be fine to say the answer is 0. 0 is a legitimate answer. The problem is this. That's what we don't want, 0 over 0. So we already know that that's not going to be the case, and we're clear here because there's a 1 in the denominator. I just didn't write it over here. So what does this become? It becomes the cosine of 0. So how do we do that? Well, we go over here and go, well, again, we're at 0 here. Cosine is always the x-coordinate. What's the x-coordinate? It is 1. So that means in this problem, the limit as x goes to 0 of sine over tangent is just 1 using identities. Now, just as a side note, let's return to the identity sheet. You're not going to, in this class, you're not going to be doing like cofunction identities, probably not sum and difference. It's really sort of crazy, some of the things that are sort of going on here. So but be aware that double angle identities might come up. So like these are the two popular ones out there. Tangent 2 theta is as well. I noticed that these are improperly written here. These are not half angle identities over here. But I didn't notice that. I'll probably delete this for next time. But just generally, just look at if you look at the angles, these are the type of things that you want to look up. That's sort of the concept of, like, when you see a trig identity, you have to refresh yourself. You have to go searching back into, things that you've learned before and see how to come up with this, see what the identities are going to be. Okay, so just back to the regular sheet here. I want to read this here because this is actually quite important for the understanding of how to do these limit evaluation problems. It says, you will find that many of these problems will test your algebra skills, but that's a good thing. That being said, it is extremely important that you realize that the expression causing the denominator to evaluate to be 0 will always be eliminated in these methods. Okay, so what does that mean exactly? Let's go up to our problems that we've worked with, and I'll get into a different color here. So if you look at, let's get rid of this. if you look at some of the things that we have done, you'll see that we always end up canceling something out somewhere. And what the whole point of our process is to do that. So, for example, here. So we know if we plug 2 in here, we get 2 squared minus 4, which is 0. That's a problem. But what exactly within x squared minus 4 is causing the issue? Well, when you factor it, you get x plus 2, x minus 2. The x plus 2 is not causing the issue. Clearly, the x minus 2 is causing the issue. Because when we sub it into that, we get division by 0. But look what happened. That ended up canceling out. So somewhere along the line, that will happen. Let's move on to the next problem. Again, if you look at our original problem here, let me get rid of all the noise here. If you look at our original problem, what was the issue? The x minus 1 in the denominator. So let's go through our problem. What ends up happening eventually? The x minus 1 cancels out, eliminating our issue. Moving on, this is more subtle. What was the issue in this problem? Believe it or not, the x in the denominator. When we plug 0 into it, we get division by 0, which is an issue. So again, somewhere along the line, that x is going to cancel out. Where did it? It actually occurred in this step. When we divided top and bottom by x, essentially, we canceled out that x multiplier in the denominator right here to get to here, and that eliminated the 0 being in the denominator. And the last one, again, what is causing the issue in the denominator here? Is it the sine or the cosine? It's the sine. The sine of 0 divided by whatever cosine is, which would be 1 in this standpoint, is causing the issue. So what ends up eliminating from the problem eventually? The sine of x. So why am I pointing this out? Because in order for you to get full understanding of this, you have to think about that. When you're doing the problem, if you are doing this properly, then eventually whatever is causing the issue is going to go away. This is something for some students who really want to understand this material more than the others, which is true sometimes. Some are just getting by. But when you look at these problems, the first thing you could think about is, all right, well, I have an x minus 1. Where is that going and how am I getting rid of it? Because if you keep that in your head as you're going through the problem, then all of a sudden, like, you're not going to make the mistake of distributing this like I told you not to. Because you're going to go, ooh, x minus 1 is sitting here. That's all ready to get eliminated. If that makes any sense, hopefully it does. But I just wanted to point that out. That's a pretty important part of the process. So let's talk about the last concept here. Okay, last concept in this lesson is called the squeeze theorem. Squeeze theorem is a legitimate theorem in calculus. We don't use it a whole lot in our class, but I'm going to do my best to explain it. Students sometimes struggle a little bit with it, but it's kind of the idea of what it is. So just remember, so suppose we have three functions, let's say f, g, and h, all right? And function values are usually y values, right? So let's just assume for argument's sake that the height of some function, let's say g, is between the functions f and h, their heights, at a certain value, let's say of x. So for all values of x near a. So right now, this is all, any type of theorem students struggle reading usually, but I'm just giving you sort of an idea. I have three functions. I have my function g, let's say, is height-wise is nestled right between f of x and h of x at some value of x. So basically what it says, the squeeze theorem, is the squeeze theorem says that if you take the limit as x approaches some value of this, and you take the limit of x approaches some value of this, and you get the same number, then if this height is between the other two, that means this limit at that value of x has to be the same. Okay, I can't explain it any better than that, I don't think. So if you're confused, that's okay. The best way to do this is using an example, as in most things with what we're doing. So that's what I'm going to do now. So it says, suppose you're given the following compound inequality. So by compound inequality, you're used to seeing something like this, right? You're used to seeing, x is between 0 and 1. Well, now we have basically a function value that is between two other functions. We don't know what those functions are variable-wise, but it doesn't matter. It's just that this is between the other two. So our goal in this problem is to find the limit as x approaches 0 of this function f of x. Now, we don't know what f of x is, believe it or not. We do not have a function for it, like in actual variables and everything. We don't have that. We only know that it's between these two. So what does the squeeze theorem tell us? It tells us that we should be able to find the limit as x approaches 0 for these two functions. So let's do that. So the limit of x approaches 0 of 1 minus x, if we sub in x, 0 for x, we get 1 minus 0, which is 1. Okay, so that was easy. There's no complicated stuff going on there. What about for this function over here? Well, let's take 0 and sub in. We get 1 plus 0 squared over 4. Again, no issues. This whole thing becomes 0, and that's just 1. So we get the two values are 1. Okay, so what is the purpose of the squeeze theorem? Well, the squeeze theorem says if you can evaluate these two functions at this limit to be the same number, then we should be able to find the limit of the function itself. So if we go back to this, we know that this is true. So let's take it down to here. So what we're going to do is we're going to take the limit of each one of these. So that's what this is. So the limit of x goes to 0 of 1 minus x is less than or equal to the limit of x goes to 0 of f of x is less than or equal to the limit of x goes to 0 of our right function 1 plus x squared over 4. Now here and here we found out that these numbers, these limits are actually 1 apiece. So what does this tell us? Look at what it just told us to begin with. It says that the limit of x goes to 0 of f of x is snugly between 1 and 1. But what does that mean that this limit has to be in that case? That means that that limit has to be 1 itself, which means the limit of that function is 1 based on the squeeze theorem, because we have effectively squeezed this limit between these two. That is the squeeze theorem in a nutshell. I think you do this on maybe once on a homework or a lab and something like that, but it's not used extensively. Maybe on an exam, be ready for it. But as long as you know the basic idea, then that is going to be that will be the key to understanding the concept.